Okay, good afternoon. Okay, good afternoon. Let's start lecture, okay? Yeah. Okay, I have this example from previous lecture that we didn't finish. So let's finish this example first, and then we'll get on to the new topic, which is the triple integrals. So it's about the moment inertia of the disk. Oh, by the way, we're going to have our second quiz next week. Okay, it's going to be on the double integral, most probably on the polar coordinates. Double integral using polar coordinates. Okay, yeah. Now next Monday, okay, it's a holiday. Is it a holiday? Yeah. Next Monday is a holiday in lieu of the Remembrance Day. But there are two tutorial sections next Monday. So what we'll do is we'll move the quiz for the next Monday section to the week after. Right? Yeah. Okay, so you don't have to go to another section. Okay. However, there's a catch, because we're going to have the quiz number 3 in the last week. So it's a little bit disadvantaged. But anyway, it's the best thing I could find a solution, right? Yeah. But the quiz, as usual, is going to be open book, open notes, and you can discuss among yourself, all right? So no pressure. You have about 25 minutes to finish one question. Okay. Okay, so let's look at this example here. It's about finding the moment inertia for the same disk, which is a circular disk with a radius of a. So what we do is we basically place the disk inside in the coordinate system. Moment inertia is always about the axis, about the rotational axis. So this is the rotational axis at here. And we basically place that rotational axis as the z-axis at here. So the disk will rotate basically about the z-axis. Okay? And now your whole problem here will boil down to basically the formula for the moment inertia. Okay, so this is the moment inertia formula. Moment inertia formula, the r at here is the distance, okay, the distance from any point to the origin. So if you pick any point to the origin, that's your r here, right? This is a circle, so we decide to use the polar coordinates. So r squared kept it here, and the dA will become r dr d theta. And then you look for the limits for r and the theta. For limits for r, what you do is you basically draw a reading line out of the origin. First contact gives you the r mean. Second contact gives you the r max. So this is basically the r max set here. And this r max, okay, we find the r max using a geometry for this right triangle. So this is the right triangle right here. The hypotenuse length is 2a. So apparently your R max, you can later basically say cosine theta equal to this R max over 2a. So R max equal to 2a times cosine theta. So this is 2a cosine theta. Okay, so that's your R max. How you find R max? Okay, this is a very important procedure here. I think I actually tested one of such a question in the final exam. When you have such a polar coordinates, how do you find R limits when R is not a constant, right? Okay, use the simple geometry to find its limit. For theta limit, you're looking at basically looking at the boundaries sandwiching this region in here. So the boundaries, there are two boundaries. One is the bottom, and the other is the top one here. So there's a lower bound and there's upper bound, right? Okay. So when you find the theta limits, you always go from lower bound to the upper bound. And this is where I mentioned the conventions has to be consistent in terms of the value for the theta. So if I go from the lower bound, for example, I go this way, say this is a negative theta, and then you go over here, this is a positive theta. So that's one consistency, right? So then you have a negative pi over 2 to pi over 2. Okay? Yeah. Another consistent way of getting the theta limits is you basically you still have to go from the lower bound first, but everything go basically one direction. So you go from here to here, that's 3 pi over 2. Keep going up to here, is 5 pi over 2. So alternatively, the limits that are here could be 3 pi over 2 to 5 pi over 2. Okay, so either way will work. Okay. So I'll use pi over 2 to negative pi over 2 here for this example here. Okay, yeah. This integral here is actually turned out to be not a very friendly integral. Okay. So let's give it a try out of here. Okay, let's see what are we going to get. So inner integral is about r here. So there's r squared times r, so it's r cubed. And r cubed, the integral of r cubed is 1/4 r to the power of 4. And then you plug in the limit, which is 0 to 2a cosine theta d theta. Okay, so now the integral for the inside, this one here, plug in the limit. So 2a cosine theta, plug it here. When you plug 0 here is 0. So you end up with basically just 2a cosine theta, plug it here, right? And 2 to the power of 4 is 16. So 16 divided by 4 is 4. So what do we end up with? We end up with just 4a to the power of 4 and cosine theta to the power of 4 d theta. Okay. So that's the results for the internal integral. Okay, the inside integral here, you get this. And then you integrate with the elastic variable, which is the theta. Now this one it's not a very basically easy integral to do. Okay, I'm going to skip this integral here. So there are two methods to tackle this one here. Okay, so one method here, I want you to take a look at, try it yourself if you want, but otherwise you can take a look at the lecture notes. Okay, number one is basically integral by part. Okay. So you're going to look at the 4 is constant, take it out, and then you have this cosine theta to the power of 4. So you separate the cosine theta, just give you one starter point here. Okay. So you separate the cosine theta to cosine cubed here and cosine theta. Okay. Yeah. And then you will use this integral by parts based on this one here. So this cosine theta d theta is d sine theta. So that's how you use the integral by parts from here. Okay. So take a look at the lecture notes. Try it yourself if you could. Okay. It's a good opportunity to practice some the previous integral techniques, right? Okay. So that's your first method. You can use this. Okay. If you do this, you end up with basically results which is 3/2, okay, pi a to the power 4. So that's the first approach. And the other approach, you can use the formula. Okay, you can use the formula. So here's a formula, you can use this one here. So a very general formula for integration of a power of a cosine function. So n here could be any number set here. And this formula says cosine n minus 1 in here, sine u divided by n, and plus n minus 1 over n, and then cosine n minus 2 times u du. So you can use this formula. It's very impossible that it will give you such kind of integral in the exam, so you don't have to worry too much. Okay? Yeah. If really such kind of thing, maybe you'll be given the formula to help you with this kind of integrals here. Okay, but anyway, so for your own interest, you can always try yourself how this integral by parts will work for this question. Okay? Yeah. So for this question, I think the important part for you is to realize how you can set it up the question. So this is how the question started, right? So you set up the question by giving it a coordinate system, basically, and then you can use the formula for the moment inertia to calculate the moment inertia. Okay. So that will be the all the contents on the applications for double integral. Okay. So if you recall that applications, we talked about the area, mass of a thin plate, the average, right, and then the weighted average of function, and then the center of mass for a thin plate, right, and then the moment inertia for the thin plate. Okay, yeah. So that's the categories we talked about for application double integral. When we finish the triple integral, we'll have a very similar, basically, type of applications that are here, except now instead of applications on a thin plate, it's going to be actually on actual 3D objects. Okay. Okay, so let's look at a new topic now, triple integral. The approach I did with the double integral, right? So I approached the double integral using an analogy, basically, to find the volume above a region R and below a surface, right? So that's double integral. So I'm going to approach this triple integral using basically not the same volume question in here, but to give it a physical, basically, meaning instead of just a mathematical formula. Okay. Yeah. So let's say consider a region D. Okay. So now consider a region D in 3D space. So this region D we're considering it here, it's actually arbitrary, basically like a 3D object. So you can draw any type of a 3D object here. Okay, consider that as a region D. So this is our region D here. So this is the first difference if you keep comparing with the double integral. The first difference now for double integral, we also have a region D, right? A region R, and that region R is it's a flat space, planar space. Okay, but region D here, okay, it's a 3D object here. Okay, so one involves two variable x, y, the other one here involving x, y, z. Okay, yeah. More precisely, I think I should put a bounded region D. Basically, okay, we're talking about not an infinite big object. It's a bounded object here. And at the same time, okay, we'll also consider a function. Okay, so there is a region D, and now there is a function of three variables. F of x, y, z. So you have region D, you have function here. Now this function, okay, is defined in region D. Okay. So let me ask a question. What does that mean? What does that when you say when there's a function defined over there? We actually described this kind of thing quite a few times already, right? Even in the double integral. So what does it mean that by a function is defined in a region D? This is actually critical. If you understand this one here, this integration concept, it will be easy to understand. Now, what does it mean by this function is defined here in the region D? Yeah. Anybody? Pardon me, it's only what?
Like the only place that exists is in the region?
Not quite. Not quite. Yeah. Yes.
For every place in point in region D, it has a defined value.
Exactly. Okay. It means if you pick a point within the region D, what does that pick a point mean? Meaning you pick a coordinates, right, which has x, y, z value. Then you plug it into this function here. You will get back a value. That's called defined. If you don't get back a value, if you get an infinite number, infinite value, like basically impulse, right? That's not defined. Defined basically means you pick a point from within this region D, you plug it into this x, y, z for the function f. You will get back a value. Okay, so that's basically what it defined means. Okay, yeah. So now what I want you to consider here is we consider a very specific case here. Just assume this function here. Okay, this function is the density function. Okay, so you represent the density of this region D, or the solid object represented by the region D. Okay. So now we wanted to compute what's the mass, right? What is the mass for the for this solid object here represented by the region D? Okay. Yeah. So then the question here would be, right? What's the mass of the object? Okay. So that's one application for triple integral. Okay, so we'll basically lead us to this triple integral now. Okay, yeah. So here is the approach that I will try to calculate the mass of this object here. Okay, so then what I'm going to do is I'm going to pick a point. Okay,
Sorry.
Oh yeah, I'm going to pick a point within this region D at here. Okay. And then I'm going to create basically a small cube around that point. Okay, create a small cube around that point. So very small cube around that point. So this is basically will give us a fairly small volume space over there, right, for the cube. Okay, you could represent a cube basically using, because it's created, okay, around a single point. So the side of the cube can be, let's say, delta xi, delta yi, and then delta zi. So there's a very small distance, okay, distance change around that point. So delta xi, delta yi, delta zi. So your volume basically for this cube is the delta xi times delta yi, and then times delta zi, right? Okay. All right. So I'm looking for the volume, looking for the mass here. So for the single delta Vi, okay, its mass is equal to the density at that location time the volume. Okay, so consider it's a very small cube, then the density around that point or inside the cube is a constant. So the mass for the little cube here will be the density times the volume here. Okay, so this is basically one small mass for one small cube. And it really depends on how you section this region D. You can section it to as many as possible, but maybe what we have here, let's see, there are only n number of cubes, okay, within this region D. So your total mass will be just adding all of the small masses together. Okay, add n number of the cubes together, and then you get the total mass, right? Yeah. But this is just an approximation. Then you can let this n go to infinite. Okay, so if you section that region D into infinite number of cubes, the summation sign here will become integral sign. And this delta VI, remember what delta VI is, right? Delta VI is delta Xi, delta Yi, and then delta Zi. So as n go to infinite, the delta sign will become D, straight D, dx, dy, dz. So this basically integral, this summation sign here will become integral sign. And we use a triple integral because now we have three variables to deal with now. So this one basically becomes derivative inside this region D, and you integrate this function and dv, right? The delta becomes a straight D. Okay, if we want to write it a little more specific, this dv is dx, dy, dz. So that's the total mass. So you got the total mass for a 3D object using triple integral, basically. Okay, yeah. So technically speaking, it's still an integration concept, right? If you are starting from your very beginning single variable function, okay? If you compare the single variable with the triple integral, it's the same integration concept. This one, you integrate this function f of x from, let's say, a to b, right, within the region. This one here, you integrate this function f through this solid region D, okay, 3D in a 3D space region D, instead of just a region, right? Instead of just what's going on here? Okay. So it's the same type of integration concept here, okay? Yeah. I approach this using a mass concept, but really when it comes to other applications, you can use it in many other different situations, okay, for triple integral. Okay. For example, here's another quick application at here. Okay. So if this function f of x, y, z equal to 1, okay, so if this function happen to be 1, then what does this triple integral become? So this triple integral just becomes this guy now, right? Just becomes this. So you integrate over the d, and then you have this, basically there's no integrand, the integrand is 1. And then you have a dv at here. So what are you supposed to get back from this triple integral? Volume, right? Good. So integration d anything will give you back that something. So that v at here represents the volume, so give you back the total volume here. Okay? Yeah. So that's another quick application, basically. Okay? Yeah. So then the next question basically is, how do I evaluate a triple integral, right? Yes.
So what's the difference between double?
Double deal with 2 variables. Triple deal with 3 variables. Double deals with a region R, which is in XY plane, or any other flat plane, right? And triple integral deals with a region D, which is a 3D.
But don't you get some volume for double integral?
Double integral, you get the volume, right? Very good point. Okay, so I guess what you're saying is, actually I would be able to answer your question when I finish this next one. So basically, here give you the volume, right? Okay, and then this one here. What does this one give us? Basically, it can also give me a volume, isn't it? Right? This is the volume. This is a volume for what? Above R and below the F. Is that good? Is that what your question here, right? This is volume. This is volume question, right? Yes. They don't conflict. Okay? They don't conflict. But this is a very special triple integral, right? Because why? Because the integrand here is what? It's 1. Okay? Yeah. I'll show you how you can actually come from here to here. Okay. So there's a very close connection from here to here. But typical triple integral, like this one here, this doesn't give you the volume. Okay? This is not a volume concept. You can consider this is a mass concept, that's fine. But this is definitely not a volume concept, right? Yeah. It's only a volume concept when the integrand is 1. This is a volume concept. Okay? Yeah. Is that good? So I'll come back to this question, for you. Okay, so now more important question is evaluation of a triple integral. Okay, evaluation triple integral. Evaluation basically means how can we carry out the calculation for the triple integral. So coming back to basically similar concept for double integral. How many different approaches we learned in terms of evaluating a double integral? Number 1, you can evaluate it within which coordinate system? Cartesian. And number 2, we can evaluate within polar, right? Okay. So we'll have a similar approach for triple integral. The first one we'll look at is, we'll look at the evaluation of triple integral in same thing, Cartesian coordinates. Okay, for Cartesian coordinates. And then we'll look at 2 other options. One is not polar anymore. One is called cylindrical coordinates, and the last one is the spherical coordinates. Okay. Yeah. So we'll look at the evaluation of the triple integral in 3 different coordinate systems. But first, let's look at the Cartesian coordinates. Okay. Yeah. And I'll use a general approach here to illustrate the steps, for evaluating this triple integral in a different, basically Cartesian coordinates, different coordinate system. First, let's look at Cartesian coordinates. Okay, step number 1. Step number 1 is you need to identify the sequence of integration, or the order of integration. Okay, so decide on the order of integration. There are only limited number of combinations because your dv equal to dx, dy, dz. So your sequence of integration can be dx, dy, dz, or could be dy, dx, dz, or it could be dx, dz, dy, right? Or it could be dy, dz, dx. So you can keep it ready. So it's a combination of 3. So there should be 9 different combinations, right? Yeah. So that's the order. So whichever you write it first, basically means you're going to try to integrate with respect to that variable first. Okay. That's the order you have to decide first. Deciding the order is not a random thing. Okay. Often in time, it really actually simplify the computation. So most of the time, you would do the z at the end. Okay, so dx, dy, dz, or dy, dx, dz. So most of the time, you do this order here. Okay? Yeah. So I'm gonna choose a order at here. For example, I will illustrate an order like this one here. Okay. Sorry, most of the time, actually you do dz first. I should say this. Most of the time you do the dz first. Okay, and then dx, dy, or dy, dx. Okay, and you actually have to look at the regions sometimes in order to have a proper orders, okay, for the integration here. So I'm gonna illustrate actually using. I'll use order dz, okay, dy, dx, okay, as my next illustration. Okay, so this is a step number 2 now. Okay, I'm going to use this, and then first, before you start, sketch the region D. Okay. If the question didn't sketch for you, and you should try to sketch this region D out. This is basically often in time. It's a practice. You know, you probably will be given region D sandwiched by a plane, an XY plane, or another plane, or even a surface, right? So, but it's not going to be a very sophisticated surface. So basically, look at the surface, and then you sketch them out, and you'll be able to sketch the region D. Okay. Now, not only sketch the region D, okay, you should also try to sketch its shadow. Okay. The shadow is basically the projection of the region D, in this case here, in the XY plane. Now see, because I choose dz, dy, dx as my order of integration, then when I sketch the shadow in this step right here, so we'll sketch basically the shadow of the region D in the XY plane. Okay? Yeah, so sketch its shadow in the XY plane. Why XY plane? Because the order, okay? This is because the order here that we decided. The last two variables of the order integration is dx, dy, or dy, dx. So the shadow here, we're going to look at the shadow inside the XY plane, okay? Inside the XY plane. And I'll give you an example right here, okay? So let's say we have a region D looking like something like this. It's more or less like a cylindrical, okay, type of object right here. Okay. Okay, so that's region D. So you have an upper surface, you have a lower surface, and there's sides of this cylindrical objects right here. So this is your region D right here. Let's say you sketch region D now, and then you're gonna sketch the shadow of the region D. So project the region D down to XY plane. So let's say the projection of the region D down to the XY plane, maybe it look like a shadow like this, just random type of things, okay? Yeah. So this is your region D. Here's your shadow R at here. Okay, so this is shadow. Okay, the shadow here. And now what we're going to do is we're going to try to label this object D and the shadow R. So for example, for this particular one here, there's a top surface. So let's call this as f2xy. And there's a bottom surface, so let's call it f1xy here. So there are two surfaces, right, for the top and the bottom of the region D. And for the shadow R, okay, it very often could be basically bounded by two curves. So let's say this side here is y equal to g2 of x, and this side here is y equal to g1 of x. So there are two curves. This is in the xy plane, right? So these are two curves, and these are two surfaces. So label basically all the boundaries, and very probably you should be able to find the x limit, okay, the boundary in the x limit here. So this is A to B. Okay. These limits here will determine the integral limits basically. Okay. So that's the step here. Sketch everything, and then label, as I said. Okay, label all the boundaries. Okay. The boundaries, not only the boundaries for the D and also for the R. Okay, so region D and the region R, so label them properly. Okay. Yeah. Once this is done, then the next step will be quite easy. The next step is to find step number 3, to find the integral limits. Okay. First, we find the Z limits, because this is our order, right? This is the order of integration we're doing. So we need to find the Z limits at here. How do I find the Z limits? So finding the Z limits, basically what you do is, okay, you draw a line, okay, let's call it M, okay, through a point in region R or in shadow R. Okay. And okay, parallel to z-axis. Okay. So this is what I mean at here. Okay, so I'll show you how you draw this in here. Okay. So find a point, basically find any point inside this shadow R here. So let's say maybe I need a little bit thicker red color here. So let's say I found a point inside the region R right here. Then we're going to draw a line, go up, okay. Apparently it's going to bump into this region D, and then it keeps going up, and it'll come out of the region D. Okay. So that's the line M in here we're talking about. So vertical line, okay, from this region R, any point inside the region R, vertically go up, okay, so through this region D. Because this is within the shadow R, so it's inevitable that it'll be it'll go through the region D at here. Okay. Then you will have a first contact point and a second contact, basically an entry point and exit point. So the first contact point will give you the Z mean, and the second contact point will give you the Z max. Okay. So that's the procedure here. So first contact will result in the Z mean, and the second contact will give you the Z max. Okay. So if you look at this particular drawing here, what's my first contact? The first contact is the bottom surface, right? So that Z mean is represented using which one? Using the bottom surface function. And the z max is represented using the top surface function. So basically here, your z mean is f1 xy, and z max is f2 xy. Okay? Yeah. That's how you find the z limits. Good? Yeah. Within the same step put it here, okay? So now let's find the x limit. So what are my second orders? The next order I had dy, right? So maybe I should find the y limits here. So finding the y limit. Find the y limits. You actually, after this step here, you're left with what? You're left with xy now, right? Yeah, or yx. So from here, actually there's no difference now from finding the limits for the double integral. What do you do with the double integral for finding the y and an x limit? So you have this region, which is the shadow right now, right? To find the y limits, what do? We draw an arrow line in the y-axis direction, okay, across the shadow. Double integral is across the region R. Then your first contact give you y mean. Second contact give you the y max. Right? That's the same process as the double integral. Okay? So that's basically this step right here. Draw a arrow line, okay, in positive y-axis direction across the shadow R. Okay, across the shadow R. First contact give us the y mean, and second contact give us the y max. Okay, so in this particular case, your y mean is the bottom curve, which is g1x, or the y2 the top curve, g2x. Okay, yeah, that's your y limits. Last step, to find x limits. Okay, x limits. So for the x limit, then you basically sweep this arrow line here, this arrow line that you just sketched or just drawn, okay, across the shadow R. Sweep that across the shadow R from one end to the other end, and find the values corresponding to the two edges. Okay, that'll give us the zx mean and the x max. Okay. Okay, so in this case, your x mean is A, your x max is B. Okay. So that's basically the procedures finding your limits for the double integral, for the triple integral set here, okay, for Cartesian coordinates. So now you can put everything together. This is your original triple integral. Okay, so now we have our order here is dz, dy, dx as the order. So your z here is f1 xy to f2 xy. Your y here goes from g1x to g2 of x. Your x goes from A to B. Okay. So that is the setup for triple integral in order for dz, dy, dx. Okay. So you can literally see that for these limits to here, right? These limits, they are determined by which one? By the shadow. Okay, so they're determined by the shadow. The first two, the F1, F2, they're determined by the region D, right? Because you go from one lower to the upper surface. Okay. Yeah. Any questions? All good? Yeah. So let's look at an example. Then we'll actually be able to be more comfortable with this. But before we move on here, I want you to actually take a second look at the process, okay, and think about what this process actually is doing at here. Remember one thing, huh? Integration is basically about sweeping through this region. If you single variable, you integrate from A to B. What do? You basically you sweep through from A to B, right? Without redundancy. You have to go through this A to B, which is we can consider is a straight line. It's a line segment. Double integral, integration about the region R. So you essentially had to sweep through this region R or recreate the region R without redundancy. And this triple integral is about integrating over the region D. It's a 3D object. So same thing, you need to basically go through or sweep through this region D without redundancy. So let's take a look at the process where we just illustrated step 1, 2, 3 here. Is that really what we're doing, actually sweeping through this region D or not? So look at the first one here, right? What's the first step? The first step, from here to here, what do we create? We create what? From here to here? We basically created one single line segment, isn't it? Right? That's the first step. What's the second step? The second step says you draw the arrow line here, right? You basically, when you go from here to here, it's like you drag this line here from one end to another end. So what does it create? You basically create a cross section in here. That makes sense, right? So it's like you close a curtain from one end to the other end, and you have this one cross section created after the second sweep. Okay. What's the next? The last sweep. The last sweep here is to sweep the arrow line across the region R. So last sweep is basically that one cross section. You move from one end to the other end, and you finish the printing of this region D at here. That makes sense, right? Yeah, without redundancy. So that's the sweeping concept that we're talking about here. Okay, it really doesn't matter which coordinate system. It's about how you can sweep through this region D, okay, without redundancy, okay, and at the same time you find the limits. Okay. Yeah. So now you can actually consider if you choose a different order of integration, and it's about basically a different way of creating this region D, right? Yeah. So let's take a look at an example here, okay? For this example, it's actually quite simple. We have a prism here. Basically, it's a tetrahedron type of shape. You have one plane intersecting this 3 xy plane, xz, and then yz, and we're trying to find the volume, okay, for this tetrahedron. Basically, the volume, the corner piece at here, okay, volume corner piece. Honestly, if you never learned triple integral, you can still calculate the volume of this piece, right? Yeah, you can use the formula to calculate the volume. So, but let's use the triple integral concept to calculate the volume in here. Okay. Now, that back to actually the question of calculating volume. Calculating volume basically means you don't have any integrand or just a 1 at here, which will give us the volume. Okay. Yeah. And now you can look at what's the region D at here. Region D basically is that it's the corner, the capacity, the volume of the capacity there, right? That's the region D at here. Okay. So step number 1, you need to decide on the order of integration. We can, in this case here, we can still use the dz, dy, dx, which actually turned out to be fairly easy computation. Okay. Once you decide on the order, the second step to sketch, which the question already sketched for you, that's fine. But the question when it's sketched is the region D. But you need to sketch also the shadow of the region D in xy plane, because we decided to do Z first, so the shadow has to be in the xy plane. And in this particular case, the shadow, you can literally see it's the bottom of the triangle there, right? The bottom triangle. So once you nail down this region D and also this region R, then we'll be confident to go ahead and then try to find the limits for this triple integral here. Okay. So now let's find limits. But first, let's find the Z limits. Finding the Z limits meaning starting from a point, okay, inside the shadow. Then you draw, basically, you draw a arrow lines in the positive Z axis, okay, across this region D. The first step is create a line segment. So that's the first step. The first contact gives you the Z mean, and the second contact gives you the Z max. First contact is the bottom surface, which Z mean equal to 0, right? And the second contact is on the top surface, which is the plane at it here. So the Z max is what? That's right. 1 minus x minus y. Okay, good. And then we're trying to find the y limits. So finding the xy limits or the yx limits is basically the same procedure now as you're doing a double integral now. You're going to focus on is the shadow of the solid region D, which is the red portion. So you're looking at the shadow here, right? That bottom triangle. So since we're doing the y first, so you draw a arrow line in the y-axis direction, okay, across the shadow R. Your first contact gives you y mean, second contact gives you the y max. So y mean apparently is 0, and y max, okay, it's not that obvious because you do know it's on this line here, right? But the question is, what is the line equation? Y minus y, that's right. How do you get to 1 minus y? So there's a shortcut you can do, because this line is the intersection of the plane with the xy plane. And xy plane meaning the z is always equal to 0. So you can literally just set z equal to 0, and then you get the bottom line equation, which is x plus y equal to 1. Okay? Yeah. So then your y max is 1 minus x. Okay? Good. So same question, if you choose a different order of integration, you may need to use a function representing these two edges here. So you might want to exercise, what is the function, what is the line equation for this side? And what is the line equation for this side then? For this side here is what? x, is it? Yeah, x plus z equal to 1, and here is, okay, y plus z equal to 1. Okay, yeah. So finally, you try to find the x limit. Okay. So you sweep this arrow line here from one end to the other end, representing the two edges. So your x min is 0, your x max, okay, it's this point here. At that point, easily you can find it out. This is a 1, 0, 0, so which is 1 for x max. So finally, you can plug everything in here. 0 to 1, 0 to 1 minus x, 0 to 1 minus x minus y, and dz, dy, dx. Okay. That's the volume for this tetrahedron in here. Okay. So you end up with 1 over 6. What's the formula for a tetrahedron volume? It's 1/3 times the base area, right? And then times the height. Okay. So you can try it out. The base area is a triangle with edges 1, 1 on two ends. So that's 1/2 times 1/3. The height is 1, so it's 1/6, right? Yeah. Okay. Okay, so when you do the integration in here, just make sure that when you integrate it with respect to z, you are treating the x, y as constant. Okay, and then same when you integrate with y, then you treat x as a constant. Okay, so there's no difference in terms of the comparing to the double integral here. Okay, so let me get, oh, he just left. Let me get back to his the question he just raised there. How do you get basically see that this is basically the volume here, right? This gives us a volume here, and this one here also give us a volume concept, huh? Right. Okay. Yeah. So here's a connection in here, huh? Here's a connection. Okay. So if you look at the drawing I gave here, I want you to consider here's a region D, huh? So the region D is the object between the region R and the top surface f of x, y. It's okay, right? This is the region D. Okay. So the R here basically it's a shadow. Okay, it's a part of the shadow of this f of x, y here, but it's a shadow, something like this. Okay. Yeah. So now if this is region D, so let's take a look at these two, right? These two actually talking about the same thing. So if I starting from here, okay, start from here. So what do we do, right? We said we basically wanted to determine on the order sequence first. So I decided to dz, dy, dx. Okay. So then what's going to happen next is within the region R, then you draw an arrow lines, okay, from the bottom to the top. So that's going to give us, what's that going to give us? It's going to give us basically the z limits, isn't it, right? Okay, the z limits. So the z limits that are here give us a 0 to what? From bottom to the top. The top is the surface, which is f of x, y. So this is f of x, y here. Okay? Yeah. Sorry, started it without you actually. So I'm just readdressing your question here. How this volume here actually turn into this volume in here, right? Yeah. So I give an example. Basically, it's your region R here. You have a surface f of x, y there. Okay, and let's define the region between this top surface and above the region R is the region D. Okay, Now, if I wanted to calculate the volume of the region D, I start from the triple integral here. Then, if I decided to dy, dz, dy, dx, so I draw this arrow line in the z-axis direction, right? Then the first contact give you here is a 0. Second contact is on the surface, is f of x, y, right? Yeah. So I'm going to skip the limits at here. Then, what does this the most internal integral give us? It gives us just basically f of x, y, isn't it, right? And then the rest of here is dy, dx. So now you see here, this is basically the double integral, right? Double integral we're talking about. Okay, so that's the connection. Huh? That's the connection. Yeah. So you can turn your triple integral into a double integral under this situation when you calculate the volume. Okay. Yeah. Any questions? Okay. Okay. So let's continue here. Take a look at another example. Let's take another example here for Cartesian coordinates. For this example, it's just about finding the limits. It's not about doing the integrals. All right, so I'm going to draw another kind of tetrahedron at it here. Okay, so this is another tetrahedron. I'm going to label some of the important boundaries for you. This is an inclined surface. Y equal to x plus z. And here is 0, 1, 0. So this coordinates here is 0, 1, 0. This is 1, 1, 0. Here is 0, 1, 1. Okay. Yeah, that should be enough. Yeah. So this is the tetrahedron, and we want to find the volume. The volume of this tetrahedron in here. Okay, now think about the process finding the limits. So far, what I have talked about, it's sort of dedicated to dz, dy, dx, right? But there are, 8 other different type of variations in terms of order of integration here. So this is what I want to show you, a different perspective. If I choose a different order, then what's going to happen basically. Okay? Yeah. So let's say in this case here, okay? Here's my new order of integration at here. We are trying to do this dy, dz, and dx. So this is what we're going to do. So we're going to do this order, dy, dz, dx. So region D is sketched for you already. If your order is selected to be dy, dz, dx, so the next step, what do you need to do? According to what I just described, you need to sketch the shadow, right? But this shadow is which plane? In the zx plane or xz plane. Okay? So this is your x, this is your z, this is your y. So project this whole region, the solid, into the xz plane. Can you visualize that? So what would you be able to obtain after projecting? Projecting basically means, you had to so this side here no longer here. So project all the edges to the xz plane. So literally you should get what? The triangle. Okay. Good. So basically it's the projection of this side here, right? This side. Left side view. But then you have to label the edges, right? Label the edges at here. So what's this is a line here. What's the line equation for this shadow here then? Square? Huh? What? Z plus x equal to 1. That's right. Okay. So how do you get that? So you get that, I guess you need to look at what's available here, isn't it, right? You have this plane over here. This is a plane. Okay, the plane literally can extend it to anywhere, right? But the plane will intersect this side. What's this side here? This side here is actually also plane, isn't it, right? This side here. But this plane here, it's a constant value for y, which is always y equal to 1. So when the y equal to x plus z plane intersect with the plane y equal to 1, then it becomes, this edge here is x plus z equal to 1. Okay, so that's how you find this edge at here. Is that good? Yeah. Now sometimes this is the little trick, maybe in the question testing you, not all the information is given, then you had to find out information like this one here. Okay, yeah. It's not that tricky. It's just have to be careful there. Okay, so once you find this out now, and then we'll try to start with the process finding the limits. Finding the limits basically means starting from any point within the shadow, you draw an arrow line in that axis direction, because we wanted to do the y first, right? So instead of drawing in the z direction, this time we're going to draw in which direction now? In the y-axis direction. Okay. So that's how you draw this line across this region D. First contact give you the y mean. Second contact give you the y max. So your y mean and the y max. Okay, y max seems to be fairly simple, fairly straightforward here. So y max is just on this side of the plane, which is 1. And y mean is right on the plane, and the plane is y equal to x plus z, so the y mean should be x plus z. Okay, that's your y mean and y max. And finally, then the next you need to find the dz limit, the z limit. So within the shadow, draw an arrow line in the z-axis direction. The first contact gives you the z mean. The second contact gives you the z max, which is on this line here, which is y minus x here. Finally, you sweep this arrow line across this shadow. You get your x mean equal to 0, and x max equal to this point here, which is 1. Okay. So this is your limits at here. And then you can write down the setup for this double integral. So dy, dz, and dx. So the integrand is 1. Y goes from 1 to x plus z. Z goes from 0 to 1 minus x. And x goes from 0 to 1. Good. Any questions on this limit set here? And as a matter of fact, what do you think the volume would be without computing it. What do you think about the volume? Should be the same as the other one, right? Yeah. So now I want you to exercise this. Try this dz, dy, dx. Try this order. If this is the order, then what will be the limits for z, y, and x? Okay, so z, y, x as the order. Z, y, x. So now if z, y, x, what will be the shadow? The shadow is in the xy plane, and the shadow will be the bottom here, right? Yeah. And you will need this line right here for future reference, and that line basically is y equal to x. Okay? Yeah. So you can use this information basically to find out the limits now. Huh? Yeah, try it. If you have trouble, let me know, and then I'll help you with this. Okay? Any questions? Good? Okay. Okay, so this is basically the triple integral in Cartesian coordinates. And I'll start the next one here off, but maybe we'll not be able to finish too much. So let's look at the next one, triple integral in cylindrical coordinates. Okay. So what's the cylindrical coordinate? So let me draw something first. Here is the xy plane. Now, if I'm going to pick a point inside this Cartesian coordinates, so let's say this is a point P. Okay, here's a point P here. So apparently you can use x, y, z to represent this point P, okay, location. And you can always get that information by projecting the point P into the xy plane. So you can find, okay, this is your y, this is your x, okay, this is your z, right? That's how you locate this point P in 3D space. Okay. However, alternatively, we can use another set of coordinates, another set of variables basically. Instead of x, y, z, we can use another set of variables to represent its location for the point P. So the other set of variables we can use is this. I will draw a line from origin to this point here. Label this is r, this is a theta. Okay. So when you see the r theta, that should remind you the polar coordinates, right? We're gonna change the z here. So basically, for point P, you can either use x, y, z. And now we're gonna have a different basically set of variables. We can also use r theta z to represent its location. So this r theta z is basically called the cylindrical coordinates. Okay? Cylindrical coordinates. So the idea is essentially at this point right here, you can always use another set of coordinate system. So let's say this is your z axis here, and then you can have this is r coordinates. So this r is in the direction of this r here. And then you have this theta at here. So theta direction. Theta is always perpendicular to the r, so it's a rotational direction. So these three here, okay, right hand rule, that gives you another coordinate system, which is this cylindrical coordinate system. Okay. Yeah. So the point here is, instead of using x, y, z for evaluating the triple integral, we'll use r theta z to evaluate this triple integral. This is basically actually what we covered in the previous lecture. It's called what? A change of variables, right? The change of variables. Okay. It's just a very special change. Okay, special variable change. Now, what's the connection between these two sets of coordinate system here? Your x, you look at this one here, your x is basically equal to r times cosine theta, and y equal to r times sine theta. And then your z, there's no change, so z is still z, right? Yeah. This is the connection between the Cartesian coordinates and the polar coordinates. Okay? Yeah. So bottom line is, say when you do the change variable, or when you're using a different coordinate system now, you will replace the x with r cosine theta, replace the y with r sine theta, and replace the z with the same thing, with the z. Okay? Yeah. So now, if I have a triple integral here, let's say originally it's fxyz, okay, dv. Okay? So dv, let's say, can be anything, dx, dy, dz, or dz, dx, dy, doesn't matter. Okay. Now you will have basically a new triple integral, but you will replace the x with r cosine theta, replace the y with r sine theta, and the z is kept the same. So that integrand function f, right, should be changed accordingly. This dx, dy, dz will also have to be changed. So it's not going to be dx, dy, dz anymore. It's going to be in terms of dr, d theta, dz, right? Okay. But of course, the point here is, okay, should we have something else out of here, right, to reflect this variable change? Okay. Yeah. Now take a wild guess. How should I get the question mark? Last lecture. Oh no, not really last lecture. Really. Jacobian matrix, right? Yes, through the Jacobian. Okay. Yeah. So I'm going to cover this part in the next lecture. Okay. Yeah.